So here in the data declaration, we are telling it that we're going to give you some data. It's going to be ny elements, and the vector that represents those elements is going to be called y. So if we actually pop out to the R code, you'll see that I actually have the next section is package the data for Stan. So I'm creating a new object in R called data, and I'm passing it a list of things. Specifically, the names here, the names of the elements of the list have to correspond to these values that we're giving it here. So it's expecting a list with an element ny and an element y. So we give it a list of element ny, which is just the length of y, and an element named y, which we're just going to give it y. If I'd actually named this as z, for example, I can put z in as data, but I need to sort of rename it y in this list. So I'll leave it as is. But I'll also run that to just create that data object. So this is that's the data block. The parameters and model blocks specify what sort of model that we're going to assume for the data. So we're dealing with a scenario where we're going to assume that the data are generated from some normal distribution with some sort of mean, but then we're going to use the known population distribution, population standard deviation of 15. So if we it might be best to actually read this series backwards. So let's look at this line. We're saying that all the elements in y are sampled from, that's what the tilde means, are sampled from a normal distribution with mean of mu, whatever mu is, and a standard deviation of 15, which is the known population standard deviation for IQ test. What is mu? Well, let's look backwards yet again. Mu itself is in the parameters. It's specified as a parameter of the model. So when you put something as a parameter of the model, that means you want to do inference on it. You want to evaluate what are believable values. You want Stan to tell you, given your prior beliefs in the new data, what is sort of your new state of beliefs about credible values for that parameter. So we define it, we sort of initialize it in the parameter section, and then in the model section, we tell Stan what our current, before seeing the data, beliefs are about what mu could be. So we're saying that mu, this again is the mean of the population, might have, our beliefs about mu might have a normal distribution. Generally, we probably think that mu is probably going to be 100. Maybe I'll do this on the board because it's easier to explain. If I were to ask you about your beliefs about mu, having not seen the data whatsoever, so I'll draw an axis here, and if I put on this axis surprise, if it turned out that the true population value was 100, you wouldn't be very surprised. If it turned out that the true population value is 200, you'd be very surprised. If it turned out it was sort of 10, you'd be very surprised as well. So what you can think about is, as you go sort of trying to think of some sort of continuous distribution that reflects what sort of how surprised you'd be. So presumably, if it was around 90, you'd be a little less. You'd be a little bit more surprised. You'd be similarly 110, a little bit more surprised. And generally, we're looking for some sort of distribution that has this sort of shape like that. That looks a lot like a Gaussian distribution if we flipped it. So instead of thinking about surprise, we can instead think about the inverse of surprise, which is the probability density. You can tell I never write with my hands. So the probability density is just the inverse of surprise. So probability density is highest at the point at which we're least surprised, lowest at the point at which we're most surprised, and we can conceive of some Gaussian or some symmetric distribution around the point at which we're least surprised. Now the spread of this distribution, so pretty inarguable what the center of this distribution should be in the context of IQ scores, because everybody has lots of experience with IQ scores, and indeed the test is set up so that it should be 100 at the population level. So we want to have in terms of specifying what our prior beliefs are on the population mean, it's pretty inarguable that we want the distribution that's centered on 100. But how spread should this distribution be is a little bit more subjective. So if we had a distribution that was, say, 20, a standard deviation of 20, sort of, I guess, the more you get acquainted with this idea of using a normal distribution to specify how believable things are, the more intuitive this will be. But a pretty broad belief distribution would be achieved through a standard deviation of 20. So that means, on average, if you were to sort of look at a new population, it would deviate from 100 by about 20 degrees, so that's by about 20 points. So we actually probably expect a little less variability, but this is sort of a pretty flat prior in the context of IQ scores. So if we were to, so just to reiterate, we've got two tildes here indicating that there's two sampling things going on. The sampling on Y is saying that the data is distributed according to some set of parameters. Those parameters themselves actually represent prior beliefs. So 15 is we basically said we have infinite belief that this parameter is 15, because that's, we're just assuming that's the population it's drawn from is 15. But mu, we're a little bit uncertain as to whether this particular sample is a little bit above the standard that we're used to or a little bit below. So we express our sort of varying beliefs on where this particular population from which the sample is drawn is located by expressing a prior belief distribution. We'll put its mean at the mean of the general population that we know about, but we'll let it, we do have sort of non-zero beliefs to either side of that mean. So I'm going to save this because it looks like I changed something. What did I change? Oh, nothing really. Oh, I deleted a line. So what's going to happen? We've generated our data. We specified our model. And what we need to do in R is two steps. First, we need to tell Stan to compile the model. Again, Stan is actually written in a C-like language that needs to be compiled. That just makes it super, super fast once it's actually compiled. But we need to compile it. So this is sort of a complicated line, but what's happening is that it's going to run the RStan function Stan model. I'll just say, whenever you see this colon syntax, that's me being a little bit non-standard for R, but just more explicit. I could have done just Stan model, and R knows that the only package that refers to a function called Stan model is RStan. But there are some times, and we'll actually encounter a few, where two different packages use the same named function. Just to be explicit in my code as to what packages function I want to refer to, I have recently started taking the procedure of the standard procedure of explicitly putting what package each function is from, if it's not from sort of the base of the functions available from the base packages. So rnorm, for example, is just available in R without loading any libraries. All right, so we're going to call the stand model function, and it asks for a series of arguments. The critical one is the file. We have to tell it to use this file here, one group, one stand. But to make it easier across all of these different folders that I was creating and the different files named different things, I made it so the only file named .stan in this folder is the one that I intend on compiling for each folder. So instead of giving it the full character string corresponding to that file name, I can actually just tell it to run this function, which is list.files. And so what list.files does is it lists all the files in the current working directory. And if I ask it pattern, or if I put the argument pattern equals stan, it's only going to list the files whose last bit is .stan. So that way it's just going to automatically grab the stan file that's in that folder. And since every folder only has one stan file, and then it's going to pass that to the file argument of the stan model, and that then compiles things. Compilation takes varying amounts of time depending on sort of how complicated your model is. So I'm going to start that going. Depending on what operating system also, R may become unresponsive while it's actually compiling. I can see up in my menu bar up here that my CPU meter has gone up a bit. That's the CPU compiling the model. It's actually going to take more time to compile this very simple model than it will take to actually evaluate it when it's all compiled. So I just watch that until it's done. Yeah. Well, it will bring me back. Yeah, R will start responding again. Ta-da. Okay. So one thing, when we compile these models, very often we'll get these warnings. Unless you get if you've done something wrong in your model, like forgotten to put a semicolon or used a command it doesn't understand, it's going to give you an explicit error. It's going to give you that error very quickly so that you can deal with it and try to recompile. But if everything's okay, it's going to take a long time, and it might also spit out some warnings. You generally can ignore those warnings. They're mostly for the developers. And they're due to things that RStan relies on underneath the hood. It's actually not a big deal. So you can ignore the warnings as long as it's gone through. We can now use that model. So going back to our R code. So the way the way that Bayesian inference in general works is that you've specified a prior distribution and sort of a sampling model for your data, and it's going to try to figure out, given your prior distribution and the sampling model, what is the new distribution that represents what you should think about the data. In order to do that, it doesn't have a sort of analytic solution. What it needs to do is actually sample the sort of parameter space associated with your model. So we only have one parameter in this model, mu, so it's going to sample various points along the parameter space, and it's going to look at, it's a complicated procedure, but it involves doing something many times, and ideally, it has two sort of sections, a warm-up phase and then a real sampling phase. The warm-up phase is the Stan's algorithms trying to figure out what the sort of shape of the parameter space is given the data. And once it gets a good sense of what the shape of that space is, it then samples from that space so that you get sort of a good coverage of the space in terms of what your updated belief should be. So the idea is that you have to do something iteratively. So you have to specify the number of iterations that you're going to do this thing. And I'll show you in a little bit how to evaluate whether you've done enough. So the more iterations you put, the longer it's going to take to do it, particularly for very complicated models. Let's just put in something 1E3.
Sorry, Mike,
yeah.
For a second?
Yep.
This is probably very naive, but I didn't understand anything you just said.
Oh, no.
I think it's because I don't know where we're going with this.
Yes.
So
okay.
What are we trying to get out of?
What we're going to try to do is establish, so we previously, like not seeing any data, we can say what is our guess for what the data should be for this population. So not seeing any actual data from this population that we're observing, we're going to say that we're going to assume that it's generally shaped like the populations that we're used to, so with a center on 100. But where that center is for this given population, maybe we know that sort of given the sampling error of the IQ test, it could be 105, could be 194.
So we're essentially asking whether this sample of random numbers that we've generated, which
Yeah.
would be data out of an experiment,
Yeah.
if this sample matches the parameters that we've specified, that it could be reasonably drawn from this population that we've indicated in the model.
No. And I could see where you got that from the traditional way we think about at least the frequentist type statistics. In the frequentist statistics, you actually say, okay, there's some null model that we're going to specify. It has parameters that we can set. Usually it's set to 0. Here we're talking about 100, but you set sort of some comparison point, and then you ask, is the data we observe reasonably, like what is the probability that that null model generated the data we observe? And usually we then sort of use some logical contortions to say if the data are sufficiently rare under the assumed model, we then conclude that the assumed model couldn't have created the data, and therefore there is some other model that creates the data. Here, what we're doing is we're saying that we don't know. There's this body of research out there that tells us for a given population, what the value, what that population's mean is, and also what its standard deviation is. We're just accepting that literature's value for the standard deviation, but pardon me?
So
that's why we're just putting in the 15. Oh, no, but the standard deviation. We're accepting that the body of literature has established that all populations have a standard deviation of 15, but we don't know what the population that we've sampled from, what its true mean is. Maybe we've encountered a population that is particularly smart, and we want to know, okay, what are the credible values for if we were to sample everybody in this population, what the true mean for that population would be. We start off having not seen anything from this population with a general belief that it's going to be about 100. We wouldn't be too surprised if it was 105 or too surprised if it was 95. We'd be a little bit more surprised if it was like 120 and a little bit more surprised if it was 80. But we have this sort of established set of beliefs without seeing any data, and we want to now say, okay, having seen this data, having collected it, what should we believe now about the population that we sampled to get this data? So what we're going to get out is an estimate for mu, the mean of the population that we sampled from, and credible intervals around that to say, okay, it may not be very credible to say the population mean was 100, or it may be most credible to believe if, say, 115. It may be a little less credible to say there was 108, even less credible to say there was 105. So we'll get a distribution of belief, sort of, again, the inverse of surprise. I'll literally be able to show you as we go.
But it is a comparison.
No, it's your. So this falls in the general domain of parameter estimation.
Okay.
We just want to know we want to know what just exists in the real world. What are credible beliefs
Okay.
for what's happening in the real world?
But the
We're
purpose
not
of including the y in that, like the two
y.
elements of
So
that model.
yep, y is the.
Is
We're
that
saying
not a
is
comparison?
no. We're
Oh.
explicitly saying that y is the data,
Okay.
and it is distributed normally with some known standard deviation, but a mean, so a population
Okay.
parameter for the mean, that itself is a little bit uncertain. We have sort of strong belief that it's 100, a little less strong belief that it's 105, a little less that it's 95. So what it's going to do, it's going to look at the y's that we observe, and it's going to update this distribution around mu to establish what we should believe about mu, given that we've now observed y. So what I'm going to do is, well, actually, I'm going to start with a really high sample iteration so I can show you guys explicitly what sort of the ideal output from this is. And then we'll drop the iterations down to talk about how to detect when you have encountered or when you haven't sampled enough. So we'll use the RStan sampling function. So we've compiled this model. We've put it into an object called model. The sampling function acts for a number of arguments. First is object, and that is just the model that we just compiled. Next is data. So we package the data per stan into an object called data, so I'll just pass that there. Chains, we're not going to deal with this, I guess, right away, but because RStan has some randomness to how it sort of starts things off, it's one good practice in addition to running lots of iterations is to start at different places and then run lots of iterations from those different places. We'll just be running one chain because it's simpler to talk to you about the output from that. But in general, it's good practice to run multiple chains, so 4 or whatever. And yes, exactly. Yeah, it's again, as I said, it starts out with 2 phases: a warm-up phase where it tries to get a sense as to the shape of the parameter space, and then a sampling phase where it actually samples that shape. Samples a parameter space given its knowledge of the shape. In order to establish what the shape of the parameter space is, though, it needs to start somewhere and do like a little walk around to see what the space is like. So iter is, I'm just passing it the number of sampling iterations we've specified up here. Warm up, I could have actually excluded this. By default, it always splits the sampling into warm-up and sampling phases in half. So half of the iterations are warm-up, and then the other half are sampling. I'm just being explicit here by saying warm-up is the first sampling iterations divided by 2. So we've got 1E5, that's 10,000. Wait, 100,000. So the first 50,000 are going to be warm-up, and the second 50,000 are going to be sampling. Refresh, gives you a little like update as it goes. So I'm asking it for an update for every 10%. If I wanted it for every percent, I'd put another 0 there to establish that I want to get like a little just visual indicator of progress that frequently. And it's a good idea to always explicitly provide a seed so that if anybody were to ever come by and try to replicate your data, they can give it the same random seed. And again, because it starts at a random position in the sampling space or in the parameter space to do its first little warm-up search, it uses a random number to establish where it's going to start. And if you set the seed, it will use the same random number every time for the next people coming along and replicating your work. So we'll run that, and I'll pop over to R, and it runs ridiculously fast because it's a very, very small, simple model. You can see it says it took half a second to warm up, half a second to sample, and it's got a total of 1 second. So having done that, we've got this object called out, which presumably contains the results of the sampling. If we just ask R to print out, there's a special print method for this object. This object contains a whole bunch of information. There's a specific sort of summary table that it can print, though, and that's by default what it prints when we just ask for R to print that object. So we look at this object. It gives us some information at the top, inference for stand model, and it gives us the what the actual name of the stand model was. It did one chain, as we asked, with each iteration of 1E5. Warm-up is 50,000. Thin equals 1. We won't talk about thinning because I generally think it's not useful. Yeah, if you're interested in some nuances, thin would be something to look up. Post warm-up draws per chain, so it had 50,000 warm-up, 50,000 samples. Total post warm-up draws, that would be a different number if we had multiple chains, but we don't. So it then also gives us a little table. So there's 2 rows, mu and LP. LP you can generally ignore. That's the log probability. I think you'd have to be pretty expert to have an intuition as to what the values in this row means. The one that we're most interested, however, is mu. That's the parameter we wanted to sort of update our beliefs about. We started out with a distribution of mu with its center on 100. We now see that after updating our distribution, then the center of our new belief distribution is at 110, which actually nicely corresponds to about where we actually sampled the real data from. These two things, the SE mean and SD, aren't as useful, but more useful is these columns here, 2.5%, 25%, 50%, 75%, 97.5%. So these are the percentiles of the data. So 50%, that's the median. You can see that the mean is actually to 2 decimal places equal to the median, so it's a pretty symmetric distribution. And the range from the 2.5 percentile to the 97.5 percentile, that would reflect your 95% credible interval. Not a confidence interval. Confidence interval specifically refers to the thing you get when you're doing frequentist type statistics. The Bayesians decided they needed to sort of establish a different name, which I think is entirely appropriate, to talk about what we're, since this distribution reflects what we should be believing, it makes sense to call it a credible interval. So the 2.5th percentile is 105, and the 97.5th percentile is 115. Now, the other 2 columns, NF and R hat, are somewhat explained actually down right below. So underneath the table, we've got this line, samples were drawn using nuts. That's a no U-turn sampler. That's a particular type of sampler that is default in STAN. That's very good. And it gives you the actual time that it was done. And then it gives you a little explanation. For each parameter, NF is a crude measure of effective sample size. R hat is the potential scale reduction factor on split change. So at convergence, R hat equals 1. So what convergent means is you sampled enough to be sort of confident that you weren't actually in some stuck in some weird place in the parameter space, that you've sampled sort of appropriately the entire parameter space. And effective sample size is, again, just a measure of how many samples that you were able to obtain from the parameter space. Now, we actually said that we wanted 50,000 warm-up, but then 50,000 samples from the distribution. Why isn't this effective sample size 50,000? It's because we've tried to sample 50,000 times, but it's often the case that you don't move enough between one sample to the other, and so there's correlations in the samples that you've obtained, and those correlations reduce the effective sample size. So what you want is at least sort of, I think I'd say like 1,000 in this NF. So what you would do is you generally change, you start with probably around, you'd ask for, say, 2,000 samples. You'd observe what your NF is, and then you'd increase that, you'd rerun the model, increasing that number of iterations until your number of effective samples is at least 1,000. I say at least 1,000 because if you want to estimate the 2.5 percentile and the 97.5 percentile, you'd need at least 1,000 observations to establish what the 25th observation and the 975th observation is. So what can we, I mean, having established this new sort of belief distribution and established the sort of 2.5% value and the 97.5% value, what can we talk about in terms of our beliefs? Well, if you have a general rule that if a value falls outside your 95% credible interval, you don't consider it sufficiently credible to care about, then in this scenario, if we had the original hypothesis that the data came from a distribution that was centered on 0, we've actually managed to shift the distribution so much by looking at new data that this 95% credible interval no longer includes 0. 100. So we could confidently say that this population from which the population from which this sample was drawn probably has an above 100 IQ as a mean for the whole population. So it's really the way that people use confidence intervals is typically inappropriate, but it's this way that they're trying to use confidence intervals. Most people say, okay, if my observed confidence interval on the mean of the sample excludes 0, then I'm going to say that 0 is not a tenable hypothesis for the real value of this of the population from which I sampled. That's technically not what you're supposed to do with confidence intervals. It's not what they mean, but it is what credible intervals mean. You can make that choice, that decision to say, okay, 100 is very low on the in the distribution of the credible what sort of values would be credible. There's very few values as extreme as 100, so I'm not going to bother believing that this population from which this sample is drawn does have a true value of 100. Just to sort of reiterate that a little bit, I'm going to show you what I mean by we got a distribution of samples. So so what we're going to do is actually extract the samples from the out object. This out object contains a whole bunch of things, but what's nice is that the GGMC package has this nice function, GGS, to explicitly extract the samples and get them in a format that's easy to plot. So I'm going to get the samples, and GGMC has its own function, a self-named function, so it's the GGMC function inside the GGMC package to look at what the samples look like. So one of the different plot types that we can look at is the trace plot. This is just from one sample to the next, what the value of mu was on that sample. So I'll run that. And in general, this is showing the samples from the after warm-up has happened. And in general, you want it to be sort of as random looking as possible. So it's sampling across the space of what mu could be so ideally, we shouldn't see any consistency. When I drop the sample size to give you examples of what you should be looking for to diagnose whether you've had enough samples, you will see some problems. But more critically, if I look at this plot, well, actually, I'm going to add one here. Show the histogram of mu. we're going to do, just look at a histogram of the samples that we observed for mu. And so you're literally getting out a collection of values sampled from the distribution that you should, the distribution reflecting what your updated beliefs should reflect. So our updated belief distribution, again, is generally centered on 110. There's a few observations below 100, but not very much, and that's why that's 95% credible interval excludes 100. Again, that 95% credible interval is sort of what sort of proportion of mass of your beliefs. The 95% where the majority of your belief mass should be. So let's just pop up and just do a few tweaks to walk through what we would do to establish whether we've done enough sampling or not. So I'm going to put this as 2E2. So what that's going to end up resulting, it's going to warm up for 100 iterations and then sample for 100 iterations. So we'll try that.
What was the, I don't understand the 2E2?
So this is scientific notation. 2 means, well, 2E2 is 2 times 10 to the power of 2.
Okay.
So 2 with 2 zeros after it.
Okay, yeah, sorry.
Yeah.
I was thinking something else entirely there because of what was there before.
Gotcha. So we'll do run that. We can look at out. Here we've got very different numbers in terms of the NF. We've only got 44 effective samples for mu, and var hat that isn't equal to 1. The values actually are pretty close. It's all written to what we got when we did lots and lots of effective samples. So despite it being low effective samples, it actually is pretty good in terms of estimating the distribution. But let's actually take a look at things. Let's look at the samples we achieved. So to look at the histogram is generally going to look fairly similar, but I mean it's fairly strongly skewed. And critically, if we look at the trace plot, with that few samples, it's actually a little difficult to see the problems. Maybe I'll pump it up to 2E2. It's also entirely possible that I'll have to do the walkthrough of the diagnostics in a more complicated model, because this model is pretty simple. Oh. Go back to R, go back to the window. Oh, I didn't update that 3. Yeah, well, I mean, it's a sufficiently simple model that it's pretty decent at, like, I mean, I could see a little bit of a sort of high correlation there in terms of, like, it got a little stuck somewhere. Looks like it got a little stuck up here, but it's a sufficiently simple model that it's able to sample the parameter space very efficiently. So even with low effective samples, and it's able to get a nice measure of the distribution. Other things that we generally do is to establish whether we've sampled enough. I mean, the trace plot is okay to look at. Humans aren't very actually good at seeing these, as demonstrated by me not being able to pick out strong things here. But other things that we are better at is, say, comparing the first. Here I asked it for 2,000 iterations, so 1,000 warm-up, 1,000 samples, and what we can do is compare the first of the samples, of the 1,000 samples, compare the first 500 to the second 500. So, oh no, that's that. Compare partial is what that means. So, in general, these should lay right on top of one another, and they generally don't. So, that suggests that we haven't sampled enough, that we haven't sort of converged on the sort of known distribution. Similarly, if I look at the autocorrelation, that means the correlation, well, I'll show you the plot first. This bar reflects the correlation between the nth item and the n+1th item. This bar is the nth item and the n+2 item. So if you extend that out to up to a separation of items, of samples of up to 50 items away, generally, if the two samples is one after another, they're highly correlated. If they are if they're further apart, you'll see that they get less strongly correlated. And that's, you generally expect an initial peak correlation. This might even be 1 now that I'm looking at it, in terms of like no separation between the two. I don't know why they do that though. But you generally want this to fall off very quickly and not have strong correlations out here. In fact, the way it is right now, it is actually pretty decent. If it had gotten stuck frequently and only exploring one area of the parameter space, you then expect that there would be strong correlations amongst the data, and therefore these would be quite high, but they're pretty low.
Can you just go back and increase the number of iterations so we can see what it looks like?
Exactly. Okay, so we'll go sampleations to 5, and that should be done. And we'll get the samples. And we already saw the histogram, and we already saw the trace plot. The compare partial, I'll show that. And they're pretty much bang on to each other. I was wrong. It's not comparing the first 500 to the second 500. It's comparing the first 500 to all of them, so the partial to complete. And then the autocorrelations, this might take a little bit of time to compute. You'll see that it has this drop off here. You'll see a nice clean drop off and then very little correlation out here. That's as compared to this, where you were getting sort of wobbliness. So that's what you should be looking for when you are sort of trying to establish how many iterations to run this for.
And what's the disadvantage of saying that very high? Is it just the
Time. Yep. And that's one of the things that most strongly drew me to the Bayesian analysis, is that it's got guarantees that as long as you search for long enough, it will give you sort of ever better estimates of what you should be believing now. With very complicated models, the traditional sort of frequentist paradigm, where you're trying to find the point in the you're often trying to find a point in the parameter space that is like the very highest point in the parameter space, and there are no guarantees that you'll ever do that. It depends on like what search strategy you're doing and how long you search for. But even if you search for a long time, there's no guarantees that you'll actually find that maximum peak. In contrast with the Bayesian framework, in addition to having much more sensible philosophical foundations in terms of doing the inference that we're interested in, it just computationally guarantees that all you need is time. You don't need to be very special in terms of what sort of search algorithms you do. It guarantees, given a particular search algorithm, that it will converge on the proper belief distribution that you should have.
So I get how this works when you're, so like if we did the joint thing, we have two different models of where the data could come from. It fits this one, it doesn't fit that one. Totally makes sense to me. But I've got 30 years of thinking about p-values. So tell me, if I was writing this paper, these were real data, I just collected these data from a sample.
Yep.
What am I concluding? So my conclusion here is not that my sample was drawn from a different population than I thought it was. It's that the population is different than what I expected it to be. Like, just
Yeah.
walk
Well,
me through, what am I concluding
you'd in sort of establishing your model, you'd set up that you'd started out with sort of expectations a distribution of belief over where the mean should be for a group that generally would be supported by most people in the literature. So 100 would be a very non-controversial point at which to put the center of where you're expecting the data mean to be. And generally you'd say, I chose a spread that's allowed me to, or that's reflected a pretty broad range of expectations. And then I updated it. I looked at this new data, and that caused me to update my beliefs about where the data generating population's mean was to this new distribution of beliefs. Look at this new distribution of beliefs, and you show what the distribution is, or maybe just the bar, the error bars at the point of the mean or median of the group, and of the belief distribution, and error bars reflecting the 95% credible interval. And it would be obvious to anybody that zero now, or sorry, whatever thing that you're explicitly interested in comparing to in this one group example would not be a tenable belief given this new data. So
am I drawing inference about this sample, or am I drawing inference then about
the population from which the sample was drawn.
And so it's basically saying that what I believe about the population based on all the work that's been done before now is wrong based on my itty-bitty sample.
Yeah, and that's generally what we do in science is we try to make inferences with regards to a larger population on the basis of a sample, and it's particularly nice when we can have a sort of prior expectation that the new sample has enough information about to overturn those expectations. That's the sort of, everybody loves that scenario.
So you might be saying here,
in the population from which you sample. Maybe if you randomly sample, like in theory, the IQ test is set up so that if you randomly sampled everybody, the population that the test was designed for, so it's usually North Americans and blah, 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 but if you did a proper random sample, then you will get 100. It's just designed that way. But if you are looking in a subpopulation of that larger population, so let's go to Newfoundland and test that. That subpopulation may systematically deviate from the general population. And that's what if your unit of random sampling, so we're going to Newfoundland, but then we go through the phone book and randomly sample people from the phone book. That your new population now is Newfoundlanders who are in the phone book. And you can now generalize your results of the sample that you observed to that population of Newfoundlanders in the phone book.
So then your conclusion would be that Newfoundlanders
Yeah. Yeah, exactly. So that would be a tenable conclusion from this, that the overall expectation of 100, IQ of 100, is not tenable in this specific population from which you sampled.
It's hard not to think in the hypothetical mode. To think of, the larger population, and a lot of ifs and thens. If this sample shows that people from Newfoundland, say, have a higher IQ, that is based on if the greater population is indeed having a mean of 100, if that is valid.
So
there's still a lot of ifs and thens going on.
It may be a little bit more straightforward. So we almost never encounter this one group scenario. So it may get a little bit more intuitive as we get into scenarios that we deal with more frequently.
So it is about compiling then data. It's not just taking a large enough sample. Is it about compiling lots of data? Or that's what
in theory, you can actually do this process every time you observe a new person from that. It just makes more sense to do it in two phases. Collect all your data and then update your beliefs. But you'd get the exact same if you updated your belief every time you observed a new person. You'll get the same final distribution of beliefs out. Yep.
You get the value kind of from a sample amount
Yep.
That's based on the number of sampling.
I mean, I think I haven't looked at the relationship between the size of the data you've collected to how many iterations you'll need to sample the parameter space of your model. I haven't looked at that relationship yet. It might. They might actually, yeah. They might be related, or they might be independent. In theory, the more samples you get, more data you give to the any Bayesian framework, the more information you're getting about reality, and the result will be your distributions will be more narrow. Your sort of updated beliefs will be more narrow. But I don't know what the relation to the number of iterations to be confident that you're sampling your posterior belief distribution properly, what that relationship is. It may be independent, but it may be such that you're, I'm not sure.
Yeah, but I guess that's what I was curious about. But you answered that I'm curious to get more data into the model.
Mm-hmm.
Can you run into a similar case? Sample so many data points that you get that feeling like, a difference of 110, the mean is 101.
Right. Let's do that. 1E4, and let's set it as actually precisely emulating what we'd expect. And my understanding is that the expectation is that you don't have the same problem of large N guaranteeing rejection of the null in the frequentist domain. Here, well, let's rerun. Oh, I didn't mean to rerun compiling the model. I really should put that at the very beginning so I never rerun it when I regenerate data. So you can see it's running. Mm-hmm. Yeah, so it's the standard error, but that's a standard error, standard deviation, or standard error of the belief distribution, not of the what the y is sampled from, which we explicitly fixed at 15. The next example is actually explicitly going to estimate that from the data as well, because that's the more a slightly more standard scenario that we encounter. So once we run this, just as a little test, it allowed me to see. Oh, and there it goes. So so in the output, it's going to pull me back down, I think. Yeah. So in the output here, you see there's a column called SD. That's the standard deviation of your beliefs. It's not the standard deviation that's right here. So really, you've gone from a belief distribution of mean of 100 and standard deviation of 20 to what we had in this posterior, which I think was mean of 110, if it lets me get there before it updates, and 3. So we've gone to 110 and 3. So we've shifted and narrowed quite a bit in our beliefs about mu. Shifted because the data actually suggested we should shift, and the narrowing is reflecting the sort of amount of information that was garnered from the data. Okay, well, let's look this out. Maybe when we. Oh, right, yes, when I created data. Yeah, I actually created it such that it violated the assumption we have that the data is always generated with a distribution with a standard deviation of 15, right. That's because the next example, we actually estimate that, that value. So going back to Joe's question of with whether these Bayesian statistics are susceptible to the problem that confidence intervals in traditional frequentist approaches have, which is the larger data you have, you're basically guaranteed to start rejecting the null, even if the null is true. And my understanding is that no, that it will always reflect the confidence interval that includes the thing that's the true value with the more data. You'll never start rejecting simply because you have lots of data.
In this case,
Yeah.
what if the sample mean is
Oh, then you just get narrower and narrower over at 110, which again reflects reality. Okay. Well, then you'll get narrow. Oh, right, and then you'll just get narrow. Like there'll be a point at which you start excluding 0 and like really like start excluding 1, 101. I keep saying 0 instead of 100.
Well, I know what you mean. We don't.
All right, let's jump to the next example, which was, well, I just wanted to show that you can do inference, well, in the sense that this was analogous to doing like a z-test, where you knew the standard deviation. I just wanted to show the analogous to a t-test, where you don't actually know the standard deviation. So I'll open up the R file. I'll open up. Yeah. Oh, no.
So, you created data and that was why.
Yep. Fake data that I was going to then pretend I didn't remember what the values I put in here were. That's the.
And what's the difference between that and the y and the stan?
Well, the y in the stan. Here, let's walk through this new example, and that hopefully will clarify. So again,
I thought that was the same as
well, we're telling Stan to expect data. So I'm going to generate some data, 30 samples from 110, and from a population whose true value for mu is 110, and true value for the variation in that sample is 10. I'm then going to do inference here. I'm going to do inference on 2 parameters, mu and sigma. Note that sigma is also a real. It can take decimal values, but it has a lower, I have to explicitly tell it has a lower bound of 0, so that doesn't try to give sigma sort of -10 value, because you can't have a standard deviation of -10. Same as before, we're saying that our prior belief for what mu is in the population is going to be centered on 100. I was actually a little, I think I changed this in between things. I had it at 20 in between on the last one. And sigma now has its own sort of prior for belief. This is a Cauchy distribution. Imagine that's a normal distribution that's truncated at 0. So it sort of has a peak at 0, and then has the point at which it goes, it's halfway from the peak to the bottom is at 15. And, half width at half max is 15. So it's a distribution where we sort of believe a lot that the sigma is 0. This actually probably isn't very tenable for this sort of data, but it's a useful belief distribution for other things. And we believe a little bit that it's 15, and we believe even less that it's 20, 25, etc. So very large values for sigma are very unbelievable to us. Smaller values of sigma are more believable. And now we're saying that y should be, we're assuming that y is a normal distribution whose parameter values are these 2 things. And we want to know what should we, given that we have some y, that's presumably we've generated some y with some known values here. But when we then try to evaluate y, we'll pretend that we don't know these. We want to ask, okay, if we didn't know what these 2 values were, what should we believe about these 2 values, given some set of assumptions or prior beliefs about those 2 values? What do you think?
assuming you do something like IQ testing, how you induce prior beliefs.
Mm-hmm.
Really having a hard time getting my head around how I develop prior beliefs about a wider population of which I've only ever drawn just one sample.
But you haven't. You're an expert in your field. You can eyeball data and know, okay, that's wonky. That's not. You have a large set of prior beliefs about data that you're just not used to expressing so explicitly. And it's just I mean, there are some tricks that, depending on time, I might get to in order to sort of standardize this. I'd actually suggest over-standardize it, but you'd be very skeptical of a mean RT of 150 milliseconds in a two alternative force choice discrimination task. So you have some expertise.
And so that's all this is your best professional guess.
Yep. And often what you do is you will run the model sort of multiple times, one using your best professional guess, and then another time saying, okay, if somebody were very skeptical about what I was doing, what would they guess? Now, often a sort of the best thing to do is I'll show you a way of doing things where you are able to establish a very non-controversial prior where on the thing that you're most interested in, usually it's a difference between two conditions, where it's you put the prior as centered on 0, and that would be what the skeptical prior would be. That's, okay, we're going to start off with a prior as 0 and see what the data says as to whether we should shift that distribution of belief. Well, we'll get into that a little bit more.
And then can I just trouble you to explain again what the Cauchy distribution is? What are those values being passed to that?
Yeah, so the first value is where it should be truncated at the lower end, and the second value is sort of, it's like a normal distribution. This would be the standard deviation. Technically, if you go in R, you can look at if you want to generate random samples from a Cauchy distribution. So temp equals R, and I'll generate lots of distributions. Location is 0. Oh, sorry. This, I mean, it's very similar to a normal distribution. The first one is the location. It's a symmetric distribution, so it's got a location and then a sort of variability, or a scale, it's called. Technically, I think it's a T with a D with a degrees of freedom of 1. So it's a heavy tail distribution. I was describing it as normal. That's inappropriate. So if I sample a whole bunch and I say hist temp such that temp is greater than 0, I confused myself. I said that it was putting this at 0 means that it's bounded at 0. No, the bounding at 0 is achieved by establishing that this sigma will only take values of 0 or greater. So if I look at a histogram of random samples from a Cauchy distribution, oh, that's less than 0. Greater than 0. Well, you can have a shifted, just like a normal distribution can be shifted. Yeah. So Cauchy has very fat tails. If you had a, so like there, from this sample of 10,000, there were some samples that were out in the 100,000 range, whereas a normal distribution probably wouldn't have such a big range. Let's see. Fatness of the tails. Yeah. Yeah, normal distribution, it would sort of, its maximum value when your sample, say at 10,000, would be sort of below 100, whereas if I let's actually even look at the, again, sample from the Cauchy. Zero, 100. And, oh. So you can see the distribution of the Cauchy drops off to fast, but then it stays non-zero for quite a while, whereas if I go back to the Gaussian case, it drops off a little less slowly, but then it goes to zero very quickly. It's, in any event, it's a standard distribution to use for talking about variance components or standard deviations. You could use other things like a log normal, and then you exponentiate it. Well, yeah. If you use the log normal, it would always be above zero. And that would allow you to say, okay, I actually don't believe 0 very much. I don't believe 1 very much. I believe 10 a little bit more. So that would actually probably be a bit more appropriate in this situation where we probably wouldn't believe 0 very strongly, would believe 15 pretty strongly, wouldn't believe 20 very strongly. So this maybe isn't an appropriate reflection of what we truly would believe. I can even just change that. Normal. So it's probably centered on 15, and don't have a great intuition of what the scale means on this. Well, just so I don't screw things up from the example that I established, I'm going to leave it as this. So the only difference now between these two, the model that we did before and this one, is that we're explicitly saying that we don't know what the population from which we're sampling its sigma is. We established a prior belief where 15 is in the reasonable realm, but it might be lower or it might be high. So if I'm going to run this again, it's going to compile. Set this to 2E5 so we get 100,000 iterations. In fact, I'm going to put it 2E4 so it doesn't take quite as long. I did a mass find and replace at one point of sample to group, and I changed that by mistake. For my bar to finish. There is a way to save the model once you've compiled it. If you actually do this in your standard, like you can actually say, you can do that, and that will save the compiled model, which I probably should have done when I established these examples, so we didn't have to sit here and wait for them to compile. In any event, let's run the code, pop over, it's quick to run, so one thing I didn't do was change the directory. So it recompiled the one model that it found in the first directory, so I will change the directory. We'll sit here again. Sure. So
I know what the Y is in the R.
Yep. And what you're doing is you're telling Stan to expect some data coming in Y, and you're telling it that you have this model for how Y came about. That Y is a sample from a normal distribution with some mean and some variability. And you have some prior beliefs about what mean that is, or what means would be believable. And you have some prior beliefs about what standard deviation would be believable, but those might not be very well supported by the data, those beliefs. So you want to know, okay, what new beliefs should I have given my old beliefs and this new data coming in? And so that's really what Y is serving as. It's saying, expect to see new data, and it's going to have this form and these priors on what these things are in this form. But you look at the data and you tell me what I should now believe about the two things actually that are listed in parameters.
Okay, so if it's still taking the same data, right?
Yep.
What to believe, but then why would that influence one down?
So the things that I observe in R, in terms of standard deviations, are the things that I'm sampling is when this runs, the sampling thing runs, what I'm going to get out are samples from what I should believe now. So
So it's a standard deviation
of your
of
new
all your
beliefs.
data.
Yeah.
It's not the standard deviation of the values of the data.
Yeah, no. It's not. Okay. So now we've got, well, 3 rows. LP again, which again, I don't have strong enough intuitions on that. Then now we have mu and sigma. And their means actually approximate the means that we actually, or the values that we use to generate the data. So that's actually nice, seeing that our new belief, distributions of belief actually reflect the parameters that we used and then pretended to forget. And we've got a distribution of beliefs. So we've got a credible interval, 107 to 114 on the mu, and 8.5 to 12.5 on sigma. So, and just double checking, our hat equals 1 in both cases, and plenty of samples, effective sample size for both. We can just take a look at the, say, for example, the partial plot. You'll get a partial plot for both parameters. So one thing to notice is that the sigma is non-normally distributed. That comes partially from the fact that it's a bounded at 0 distribution, partially from the fact that our prior distribution was a positively skewed thing. But otherwise, the two belief distributions are generally very similar. And the autocorrelation, just double check that they're both pretty good. Yeah. And with such a simple model, it's even the bad plots that I showed you before weren't too bad. So these definitely aren't too bad either. So that's the sort of simple elaboration of this scenario where you're actually estimating sort of both data generating parameters. That's a little bit more typical of the data. The scenario where you encounter data, you don't have a point belief about, say, the variance. You actually need to estimate the variance from the data itself. This third example is going to be the exact same in terms of data generation. I'm not even going to run it. I'm just going to show you that if you look at the STAN data, the only difference between, here I can even open up that old file. The only difference between the model that we just looked at and this new model, I'll close the file window. So it's, 20, is that we didn't need to assume a normal distribution for y. Often that's the case in many frequentist statistics because the normal distribution has nice mathematical properties that allow the frequentists to have closed form solutions for things like the p-value and things like that. But you don't need, you can use a non-normal distribution, for example, if you had, one common thing is if you know that you're going to have outliers and things like that because your data sort of is a mixture of a normal plus some other thing, you can explicitly sort of have an outlier robust strategy of not using a normal distribution, but a heavy-tailed distribution. Cauchy would be the example of a t-distribution with a degree of freedom of 1, so very fat tails. You can use, there's actually, I believe, a t-distribution in R that you can use, so you can specify the fatness of the tails explicitly if you wanted. There's also other ways where you can actually explicitly say that it's a mixture of two distributions, a normal plus a uniform, for example. The standard way of just dealing with outliers is to just use a Cauchy, for example. And that makes it just more robust too when you have sort of an outlier that's is very far from the mean of the data, and it allows you to still do inference without having it that single value being super influential on your data. So I'll stick with the normal for all the rest of these examples, but I just wanted to demonstrate that you can use different distributions very easily. So let's move on to something a little bit more interesting. So two groups. Well, I'll just start running this to start us up. We're going to generate some data. So Y1 is one group of people. We'll generate 30 values for Y1. They'll have a mean of 97 and a standard deviation of 15. Y2, again, we'll generate 30. Mean of 108, standard deviation of 15 as well. And then we want to ask the question, sort of, are these two groups, do they have the same sort of data generating population parameters? Usually we're most interested in whether the means are the same. Here again, when we generate the data, we know their means are different, but we're going to pretend that we didn't generate the data, that we sampled them from some unknown populations, and we want to do inference on whether the means are different. We package up the data in a certain format for Stan, and then we compile the model. So I'm actually going to compile the model while I talk about it. Double check that it's going. Yes, it is. Okay, so to talk about it, let's open up the Stan file. So data coming in. We've got two groups now, so we want to know how many people are in Y1, how many people in Y2. Implicit here is that sort of the example we have is 30 and 30, and most frequency statistics work best if there's equal numbers. Here it doesn't matter if there's equal numbers, you can have different numbers and all the inference works out just fine. And you're passing it into vectors of numbers, one representing the Y1 data and the other representing the Y2 data. And in this example, we're going to assume, as is typical in the tools that you've been exposed to in sort of the frequency domain, that the two groups have the same error variance. So they're generated from distributions with the same number here, so 15 and 15 for both, but that they may differ in terms of the value of their mean for the population. So they might have different mu values. So down here, you can see the two sampling statements saying Y1 is distributed normally with an error of sigma and mean of mu1. And then if we look at, okay, what did we actually believe about mu1 in the first place? Well, it's normal with the, let's change this back to 20 where I had it before, because it's a little bit, a standard deviation of 5 on the belief for population is a little bit actually, that's a very strong belief here. That means that you don't really believe that a population will have, say, a mean of 110. So we'll believe that this population for Y1, without observing any Y1 data, it's centered on 100, and it has sort of a pretty broad variability in terms of what we believe. So 110 would be an okay, decently tenable belief. 120 would be probably less tenable, 140 even less tenable. Similarly, Y2 is sampled from a normal distribution. same sigma has y1, but a different mu, or a possibly different mu. But the belief we have about mu is exactly this that we established on mu, and without seeing any y2 data, is exactly that we established on mu1 without seeing any y1 data. So we start out believing that basically these two groups were sampled from populations that had the exact same value for where their mean is. Looking at so it compiled, and in theory can go back to the R code. I think I need to run that. Double check it. No, I need to run all this. And now I'll go 2E, and I'll just do 2E4. So look at out. So now we have 4 rows, LP, sigma, which we don't, well, again, this is common to both. The mean was 15, so it's very close, sorry, mean was 13, very close to 15 that we actually used. It's probably, the fact that it is a little bit lower than what we actually used to generate the data might be, well, yeah, it might be due to the fact that we used that very, prior belief distribution on sigma that is peaked at 0. But otherwise, it has sort of a reasonable interval around the values that we actually used. And then we're looking at the mean from U1 and the mean from U2. Notably, they're different, but close to what we actually had, 97, 108, 98, 108. They're confidence intervals, sorry, credible intervals, exclude one another, just barely, but they do. So you could take away from M that R hat is 1, effective size is up in the thousands, so we're pretty confident that we got a good estimate of this, the endpoints of the credible interval. So from this, we could say that the belief, the distributions of belief for each of these populations respectively exclude one another pretty substantially. There's not much sort of mass in the overlap between the two distributions. That's one way of doing this model, actually explicitly having 2 mu values and looking at the two populations that way. Better though is, I'll keep that open for a second while I open the next one. If you look, the R file is exactly the same. So we're doing 2 distributions, but, and we submit the data in the same way. So if I compare, let's close the R file and just field toggle between these two. So this data generation block in the new one, same as data generation block in the old one. Not data generation, but specifying what data is coming in. So it's the same. But in the parameters, we'll see that in the old one, we've got mu1 and mu2 and sigma. In the new one, we've got a mu, a diff, and a sigma. So what this new mu means, it's the center point between the data generating populations means. So we're sort of assuming that these data generating populations are normal. So you could call it, it's the mean of the 2 means. Using center point, so I don't have to say mean so much. And diff would be the difference between the data generating population's mean. And mathematically, this works out to be exactly the same, but it's just conceptually easier to think about it this way, in that we can talk about, okay, our prior belief on the center point between the 2 distributions. So let's say it's a normal of 100 and standard deviation of 20, like we had before. And then we can then talk about the thing that we're actually most interested in explicitly, which is the difference between the 2 populations. So we say that that is distributed, our prior belief for that is a normal distribution centered on 0 with, let's actually bump that up because it's probably a little bit more reasonable to have a more broad distribution of beliefs. But then otherwise our sigma is the exact same. So then when we want to talk about what is y1 distributed as, so y1 is distributed as a normal distribution with a mu plus this difference divided by 2, so half the difference, and y2 is mu minus the difference divided by 2. So this difference actually could be signed. So if it's a positive difference, then y1 being mu plus difference, y1 will have a mean greater than y2. But this difference alternatively could have a negative value. So if you have a mu plus a negative value, it means y1 will be less than negative 2. Or sorry, less than y2. Well, again, what I'm saying is that since we're centering the difference on 0, it will work out the signs by itself. The fact that I'm saying mu plus diff, mu minus diff, I was intending to, by that little sidetrack, just saying that these signs don't actually matter. I could do it the other way around, and we'll get the same sort of results out. It'll just change the sign of what diff is. So if I'd run that, well, yeah, I'll go I was in theory going to compile. Meanwhile, I'll change this to 2e4 and have this go. Ideally, what's going to come out is it's going to have mu of 102. Yeah, that's the, sorry, 103. And it's going to have a diff of 10. So we'll get an explicit distribution on the sort of what we should believe about this, where the center point is. And we'll get a distribution on the thing that we're actually most interested in, which is what we should think about in terms of the difference between the two groups. And this is where we get sort of into the analog of what people are used to in the confidence interval world of saying, does the confidence interval include 0 or not, to make sort of decisions about whether you should accept the null or reject the null. Here, we're going to have a 95% credible interval on the difference, and if 0 isn't in that 95% credible interval, it's unreasonable to believe 0, and so it's reasonable to believe values that are non-zero. Okay, so I said 103, it's about 104 for the intercept, the center point. It's got this general distribution, but critical, we're looking at the difference, what we should believe about the difference between the two groups, and its distribution ranges from -18 to -4, so excludes 0. So 0 is not a very tenable belief for the difference between the two data generating populations, so it would be reasonable then to also believe that non-zero is the true value for the data generating population's difference is non-zero. So writing this up.
We're not distinguishing here between how the data is reflected. So when we do an overlay, but repeated.
Right. Yeah. We haven't gotten to repeated measures yet. No. Here we're just talking about two independent groups. All right. Let me just check this. Mu is like the intercept of the model. It's really a thing that we're not too interested in. It's a way of, so here we've got two distributions, and we kind of have to eyeball what and we're interested in their difference. So we kind of have to eyeball their difference. Here, it separates out, well, whenever you have two things, two groups or 2 points, you have to use two numbers to describe them. Here, you literally describe each one by its own number. which means that if you're interested in the difference, you have to actually like infer something. Whereas here, you are using one number to describe the thing you're interested in, and then another number to absorb the rest of the stuff that you need to position it properly in the data, or in the data space. So this is actually the parameterization that sort of is more standard and more typical, because again, it has an explicit number reflecting the thing that you're interested in. The next example shows it's the same general idea. Yep. Oh, I come back. In theory, if you sampled a lot, yes, I could actually. Yeah, yeah. So you can actually always convert from one format to the other afterwards once you've got the samples. So I had samples for mu1 and samples for mu2. I could have, for each pair of samples that I got in the output, I could have computed the difference, and that would have given me what I have here, which is the difference distribution. Because it's random, because there's random start points, and the way you parameterize it somewhat influences how it searches the parameter space, the shape of the parameter space that it's searching. There can be slight differences, but in such a simple model like this, even with a few thousand of samples, they're going to be almost mathematically identical in terms of what confidence interval you'll get out, credible interval. So the next example is an example where you have data formatted a little bit more. So it's really rare to have data when you are coming into R where you have just like a list of values for one group and a list of values for another group. Much more typical is you have something more like a list of values all in a row. So one column with the measured value, one column, and then another column with like group 1, group 2. So actually, I'll show you a bit better here. So. It's much more common to have data like this, where you have, in fact, let's see that over here. Something like this, where you have, here's one person in group A, here's another person in group A, here's a third person in group A, and then further down in your data, another person, sorry, here's a person in group B, here's another person in group B. So this is called long format data, where you have the data sort of all in one chunk, and you have different columns helping to specify the different sort of variables, the labels associated with each data value. I've got a column here called X, and this is just a numeric coding for what's in this column. So whenever you see an A, it should be negative 0.5, and whenever you see a B, it should be positive 0.5. That's called a contrast. Whenever you do any sort of analysis in R that involves like something like this, where it's a letter in the column, R will, behind the scenes, automatically convert that letter to a number in order to compare, say, if you just have two groups in this column, it'll turn that group column into a factor, and then when you do, say, a linear model, Y as a function of group, it will automatically create, sort of behind the scenes, a numeric value for each thing in the group column. So I'm just showing it a little bit more explicitly because Stan wants to see that. look at the model. So I'm telling it how many, in terms of the data that I'm packaging together to give this Stan, I'm giving it the number of observations total between the two groups. Again, here we're not assuming equal number of groups, we just happen to have put in equal numbers. We just give it a single vector representing all the y's and then all the y1s and then all the y2s, and then as the vector y, and then another vector x representing the labels, and specifically the contrast coded labels for each group. So again, all the y1s are -5, all the y2s are 0.5. Usually, you won't have to do this by hand. It'll automatic, like your data will already be in long format. And so I'm just showing you this so that you can see how you would deal with long formatted data in Stan. So you tell it how many y's, how many observations you have across the groups. You then give it all the y's. You then also give it all the contrast labels. But then otherwise the parameters are all the same. You've got mu, you've got the difference. This is again that sort of center and difference parameterization. All these are the same. I think we decided that we wanted to broaden these to. And here, instead of talking about y1 is distributed as and y2 is distributed as, we just say y is distributed as. And we can say mu plus diff times x. And because x is just a vector of 0.5s and -0.5s corresponding to what condition each one is in, that works out to the same as what we had before. Where for all the ones that were y1, we said plus diff divided by 2, and all the y2s we said minus diff divided by 2. Does that make general sense? It should be the exact same math. It just is the structure of how we're giving it the data is a little bit different. So when we get down to actually talking about y1 and y2 being differently distributed, we have to refer to the vector encoding like what condition a given value is in. So I won't actually run that because it comes out having the same values as we just did, because all everything in the parameter block is the same, and everything leading up to that y is the same. So we'll get the same values out. That was, I think this one is the same, where we end up getting long formatted data. The only difference is that in generating the data, I actually generated them from populations that differed in their standard deviation. So remember, in the standard 2-sample t-test, we've got two groups. We're mostly interested in whether they differ in their means, but you have to make the assumption in order for the math to work out, and in order for the math to work out, you need to make the assumption that the two groups have the same standard deviation. This is an assumption that our data often fails, and we have tests of whether you meet that assumption. But in Bayesian world, you don't need to make that assumption. You explicitly estimate whether there's a difference between the two groups in that sigma value. So I'll take a look at, compile while we look at what we do. So the input data is same as above in terms of we've got a long format. So we've got y as the sort of observations, x as the predictors. It's just -0.5 for y1 and +5 for y2, +0.5 for y2. We've got the same as before. Instead of, I think I had it as mu and diff. So here I'm being explicit and saying mu center and mu diff. But here we have, instead of just a simple sigma, we have two values, log sigma center, log sigma diff. So first of all, why log? Well, if I want to talk about there being a difference between the two groups, I never want that difference to be such that one group is 1 and the other group is -1. So if you want to implement some sort of center difference parameterization on the sigmas, you need to have a sort of do the difference on the log scale, and then when you exponentiate that, that makes it so that it's always positive, because you always want your standard deviations to be positive. I could, in fact, have just done it y1 sigma and y2 sigma. That probably would have been a little bit more straightforward for you guys to see. So actually, let's actually do that. So y1 sigma. Oh, that'll screw up my having pre-compiled, won't it? Well, otherwise, in terms of the mu, everything's the same. I'm just naming them a little bit differently in terms of, instead of mu and diff, we've got mu center, mu diff, and this is all the same as what you just saw in the last model. What's different is that we've got this here and these two here. And what this effectively does is it says that's the sigma that's going to be applied to each group can be different. And it depends on we have a prior on what the sigma should be. I guess on the log scale, it's going to be centered on, well, 10 on the real scale, but with a little bit of variability on either side. And we also have a prior for whether there's a difference between the two groups, and I just put that as centered on 0. So we mostly believe that there's no difference between the two groups, but we have some reasonable amount of belief that there might be a little bit of difference, but we don't know which way. The end consequence of having this means that we can sample and have a actual estimate of what the variable does not exist. Oh, I didn't run this part. And then I undid it, yeah. Oh, I would have, yes, you're right. Yes, I would have. Because these variable names are very long, it pushes the number of columns that I can show off. So you'll see it continues the table down here. But critically, we've sort of approximated we've got the same sort of differences between the two groups that are approximating what we actually implemented. But we also now have estimates for whether there's a difference in their variation or not. This is on a log scale. Ideally, I would have made it so that it automatically exponentiated it so that we could see what the actual thing is. In fact, if I recall correctly, the R code does this. Let's go take a look at it. Where'd it go? Okay. So to actually look at what those standard deviations are, we first get the samples. We can look at like the partial plots to see, do those shapes generally match up? They generally do. And just doing the autocorrelations, and those generally look okay. And this will actually just do this is just standard R to go through and get what for each iteration of the Bayesian sampling, get what the center value was, get what the diff value was for the log sigma center, log sigma diff, and then explicitly estimate or explicitly compute what the cell 1 sigma would have been, what the, sorry, y1 sigma would have been, what the y2 sigma would have been. I call them cell 1, cell 2. And then compute the difference on that real scale instead of the log scale. And then it's going to finally summarize those by saying what the y1, what the 95% credible interval on the y1 sigma was, and what the 95% credible interval on the y2 sigma was, and what the 95% credible interval on the difference between those were. I'll leave you to figure out what the actual R code is here. It's using a combination of plier and dplier and this nice chaining to this. If you get into R anymore, this is sort of the future of data manipulation, is chaining things together. It makes it a little bit more readable once you know what you're looking at, and a lot less code that you have to write. So let's actually look at what comes out. So what it's saying is that this is the 2.5 median and 97.5 points. So we had, when we generated the data, I think up here, 10 and 20 as the data generating standard deviations. So how close did we get? 9 and 16. So it's a little bit underestimating what the 20 was, probably because we had that prior belief distribution that's probably not appropriate, where it has maximum belief at 0. So it should be pulling larger values of the standard observed standard deviation. We'll get a posterior belief distribution that's a little bit closer to 0 than where the sample standard deviation actually is. But generally, we can see that it actually appropriately saw that there was a difference between the two groups in terms of what their data generating standard deviations were. So again, another way in which sort of the Bayesian framework is very flexible to things that would generally break the frequentist framework. So, next one walks through sort of a generalization of this idea to 3 groups. So I'm going to run this stuff. All the way to here so that it starts compiling the model. So what we're going to do, we're going to have 3 groups now. We're going to generate them such that they all have a common standard deviation, and in the model we'll just assume that they have a common standard deviation. We'll code it so that they actually do differ. So 1 and 2 do differ, but 1, 2, and 3 don't. And we're going to package it up together sort of in a long data format. So y is just a vector of y1, y2, and then y3. So its length, the number of y's is just the length of each of them, the sum of the length of each. And because before we just had one group, so we just passed it a thing called x that represented the contrasts of y1 versus y2, so negative 0.5 and positive 0.5. Here, we need, because we have 3 groups, we need to supply 2 contrasts. So the first contrast is just going to be the same contrast that we had before, where we're comparing y1 and y2. So for the first length y1 items, it's going to have a negative 5. For the next y2 items, it's going to have a positive 0.5. And for that contrast, it just completely ignores the, that should be y3. It just completely ignores all the y3s. And next, to have a contrast that's sort of orthogonal to the other ones, that previous one that we had, it's a little bit weird, but what you do is you say y3 compared to the mean of y1 and y2. So I could do it a different way. I could say a mean for y1, a mean for y2, a mean for y3. But as I showed before, just having a mean for each condition means that when you're when it comes to looking at the things that you're actually interested, which is differences between conditions, you have to start doing inferences. You could just compute those differences in the sample. But when you're setting up like the priors for the difference, it's a lot easier to set up a model where you're saying, you're talking about where the data is centered, and then independent of that, what the differences are. So that's what this sort of contrast coding will achieve. The first contrast will code the difference between the first two levels of y, and the second contrast will code this orthogonal contrast, which is the difference between y3 and the mean of y1 and 2. And when we look at the actual model, we'll see that so we've got the data coming in. We have to tell it how many data points there are, give it the data points, give it the two contrasts, the vectors representing the two contrasts. But otherwise, it's similar as before. We've got a parameter that represents the center point between all of the data generating distributions, a parameter reflecting the difference between group 1 and group 2, and a parameter reflecting this weird other contrast where we take a mean of group 1 and group 2 and compare that to group 3. But critically, this allows us to just say, we assume all the differences are centered on 0, and we'll assume that the groups as a whole are centered on 100. And again, we've assumed that all the groups have this common sigma, which is pretty typical, but I've shown you how to relax that assumption and look at effects on sigma as well. And when it comes to looking at y and establishing what its value should be, it's normally distributed with an error of sigma and a sort of mean that is mu, the overall mean for all the groups, plus diff1 times this contrast plus diff2 times this contrast. So this is actually going to come out to 0 for all the rows in which contrast 1 is 0. So for all the group 3 folks, they have this as being equal to 0. But this then will, well, I guess, ignore what I just said there.
Mm-hmm.
This mathematically works out so that we can get sort of orthogonal, these are orthogonal contrasts, and they implement the centering difference in the case of more than just two groups. So if we actually go back, that's run, so I can run that. Look at R. It's starting to go a little bit more slowly now that we've got sort of increasingly complex models. We'll get out posterior distributions for sigma, diff1, diff2, and mu. So mu, that's sort of a easily interpretable value and sort of where generally the groups are scaled. Diff1 is also sort of easily interpretable in terms of, well, is group 1 different from group 2? We implemented that they were, and indeed the 95% confidence interval, credible interval nicely captures that difference. The difference between the mean of 1 and 2 and then 3 is less sensical, partially because we know we implemented it so that 2 and 3 are the same, but 1 and 2 are different. So this this difference contains both of those things. So better would be to take a look at, grab the samples, and we can explicitly look at each of the pairwise differences. So we actually explicitly go through, get the estimate each iteration would have had for each group by just multiplying out what those contrasts were. And then we can look at what the each group versus each other group would have been. if I recall correctly, I think if I do this as that, don't even need those two things, do I? Yeah, it's probably done anyway. So group 1 versus group 2 shows that same interval we would have had up there. 783 as the median, probably just numerical precision error. Oh, 7839, so that's the same as 784 there. So, I mean, in theory, these should be the exact same numbers as up here, and they probably are. 2 versus 3, so these two things give us new information. 2 versus 3, well, its credible interval is pretty well centered and encompassing 0. However, 1 versus 3 is pretty similar to 1 versus 2. So that's the exact sort of setup that we generated data from, where 2 and 3 were the same, but 1 and 3 and 2 and 3 are different. So that gets us out the data that we generated. And I mostly just wanted to show you that from the perspective of what you do when you have more than 2 levels of a predictor variable, that you have to start creating these orthogonal contrasts like this. And that allows you to maintain this center difference coding of the data. Yeah, the only point was because you need 3 when you've got, again, when we had this scenario of 2 groups, I needed 2 numbers to reflect the data that there's 2 groups. So you could either parameterize it as group 1's mean and group 2's mean, or you can parameterize it as a center point plus a difference. That center point plus a difference actually is a little bit more intuitive for what we're doing scientifically, because we're really only interested in the difference. With 3 groups, you need 3 pieces of information. You could either just have mean group 1, mean group 2, mean group 3, or if you want to maintain this difference, center difference parameterization, you can. In this case, it's a little questionable whether you want to go with through all that trouble. I like that you can, if you maintain the center difference, you can always use difference distributions for the prior on the difference distributions. You can center it on 0. It gets a little bit, well, easier when you start talking about like interactions and things like that, when you have multiple variables, where the center difference parameterization is easier to use. But in this case, I was showing that you can maintain that center difference parameterization even when you have 3 groups, but you have to do it a specific way, which is to make this this second difference score that is weird and not really that useful unto itself.
So it's just there to like allow that.
Yeah. As we show, you actually have to do some computations afterwards to actually get out things of interest, like the differences just from one group to another. Is this any use? This next example is the same data. So I'm just going to compile the, but you can actually, instead of having, this is mostly a time saving for your fingers that, well, I also wanted to start introducing you to the idea of instead of having a variable for each, a parameter declared for each thing that you want, so the mu, the diff2, you can actually put them all in a matrix, and it just is a little less typing. Similarly, but what you have to do then is you have to use matrix algebra. So I'll step through this. Let's just jump back quick to review what we had for, again, this 3-group scenario with mu and diff1 and diff2. You then had to specify a we had a lot of redundancy where we had to sort of say the same normal distribution on both of these, and then you actually had to do a lot of typing to say, okay, mu plus diff1 times contrast 1 plus diff2 times contrast 2. Instead, we're giving it, again, that vector y, but and we're giving it a matrix called x. And how we created that matrix in R would have been, we had one column that was just all ones, another column that coded for the first contrast, another column that coded for the second contrast. Here I created it as a data frame just for ease, and then I turned it into a matrix. So this matrix has 3 columns, and those columns actually correspond to the 3 separate things that we had to create here. So instead of having to create 3 separate things, I just create one thing here called beta. It's going to have a length of, so nx is passed in as the number of columns of x, so 3. I know the first element is the intercept, and I want to specify special prior for that one, so centered on 100. But for all the other columns, all the other diffs, I have this other prior that I want to apply to it, so centered on 0. And then sigma is just the exact same as before, so calculate distributed, and just put here is common for all the ones. And so now, in terms of just what sort of arithmetic you have to put to make each y group assigned the right mean here, you just have to multiply this input matrix of coefficients times this beta vector. And that yields the same result, mathematically the same result as having all these different things, a separate mu, a separate diff times the contrast, a separate diff2 times the contrast. This will achieve the same result in the end. So what did I run up to here? Okay, so yeah, that one. There. So Caitlin, I was just showing that the second example for 3 groups has the same functional outcome, except it's just a little bit sort of briefer to type and to show. Instead of having 2 contrasts as inputs, and then 3 parameters that we're estimating, mu, diff, diff2, and then all these priors and this complicated specification of the means for each group, we are able to have a single matrix as the input to hold both a column for just ones as the intercept and then the 2 different contrast columns, a single vector holding 3 values, the number of columns in x, 3 values to represent the sort of coefficients that we're estimating. First coefficient is that intercept. We estimate it as a normal centered on 100, and then the other 2 intercepts in the this matrix are given the same prior distribution. And then finally, instead of all this, all these sums and multiplications to set each y group to its proper mean, we just can say x times beta. So,
Didn't follow how beta got in there, so can you? That's okay.
yeah, it comes from here, and I have here I'm sort of setting the priors on what beta is, and here it's using beta times the input we have. So it's just doing matrix multiplication. So what it does is it goes through and for each y, it looks at what is in that row for x.
Okay.
It multiplies 1 times the first element of the entry for the first column in x times the first, I guess, entry in beta. Whatever's in the second column for x times the second entry in beta. Whatever's times the third column in X times the third entry in beta, and then sums the result, which is the exact same as what we had here, where we had a mu times diff times the contrast.
I totally understood that one.
Okay. So we'll just take a look at what that looks like. And here, the naming is going to look a little bit different. I did it. I told it. Oh! I told it to remove everything from memory right after I pre-compiled it. In Stan, we initialize an object called beta that's going to contain the each of the coefficients. So it's going to contain the intercept plus the coefficient for the first contrast plus the coefficient for the second contrast. So I'd said that we'd meet for this week to try to wrap our heads around various models for Stan, and then try to work on our own problems over the weekend and meet next week to see how that went. Given that I didn't get through to the, well, there's a few more that I think are important to get you to the place where you're looking at the types of data that you're actually going to be dealing with.
Yeah.
Maybe I'll get you, your homework is to go back through these and try to make sure that, try to refresh your memory for what the hell is going on in each of them, so that you have, so that we can come back to, and start with these ones that get even more complicated. Yeah, yeah. Maybe, so, okay, so that compiled. We can, actually doesn't matter which one of these. So, now, before we had a mu, diff1, diff2. Now we have beta1, but that just corresponds to mu. Beta2, that corresponds to diff1, and beta3, which corresponds to diff2. And otherwise, it's the exact same. So remember that we had that diff1, which was a nicely interpretable difference between the first group and second group, and diff2, which was less interpretable. And do I have code down here to actually, oh yeah. So in this table, you'll see that it's got beta and then in square brackets, 1, 2, 3. Eventually, when you get the samples out, it gets changed to period around the numbers, but otherwise, this will go really fast. Yeah. So otherwise, you get the exact same numbers as we had before for the comparison. It's again just that this. I mean, technically, I think that the multiplication runs a little bit faster. Sorry, the matrix version runs a little bit faster. Let's actually see. Oh no, it's a little bit slower. But when you get into more complicated models, it's a lot less typing when you start having the matrix. So when you start looking at scenarios where you have just like a 2x2 or a 3-way, or I guess 2x2x2, there's a lot of contrasts that are implicit in that, and being able to just put them in a matrix and not have to type them all in and type in, just let it do all the matrix multiplications to work out what each group should be is much easier. Yeah. Next 3 groups. Well, I'll end with this one, which is the a version where so far we've only been doing one-way versions. So here's an example of an interaction. Clear all this. I'll actually run all this, and then I'll come back and explain it so that I have this compiling. Okay, so generating data, 4 groups, each of 30. Could have been variable numbers of people, each at 15. So we're going to impose an assumption of sort of homogeneity of variance. But we've got A1, A2, B1, B2. So it's a 2 by 2. We're going to do the matrix way because it's just a lot easier in terms of what to write in the stand code. It's a little bit more cumbersome to write when you're doing the creating the data from scratch. But if you have data that you've already read in, it's very easy to generate these contrasts just from what your factors are in your data frame. But I'm generating these. So I create a data frame called X. There's one column that's just all ones, and that's going to code for the intercept. Got another column that's going to code for a first contrast. So that's for the A versus B, so -5, -5, 0.5, 0.5. And then the next contrast is 1 versus 2, so that's -0.5, that's -0.5, and this is 0.5, and this is 0.5. So we've got one contrast for A versus B, another contrast for 1 versus 2. And then if we want to look at an interaction there between, all we have to do is actually a third contrast reflecting the interaction is simply the product of these two contrasts. So then we finally convert that to an official matrix instead of a data frame and put everything together in a list. So all the y's together. So well, how many data points are there? Well, we just get the length of all those. How many predictors are there? How many contrasts are there? Well, we put that in there. What are all the y's? We put them in sequence. And what is the x? And we created the x up there. So let's take a look at what the model actually will be doing. Well, it's a pretty simple extension from what we had before. It's the exact same data input as before. We had a matrix X, it has some number of columns in it. The exact same parameter set. We've got a vector beta with some number of elements to it. And otherwise, it's actually the exact same everything else. So we want to have we have some sort of good prior information that the intercept should be around 100, but then for all the rest, so the main effect of one, the main effect of the other, and the interaction there between, we'll just put sort of skeptical priors of centered on 0 with some amount of variability around 0. So this is what's nice about the matrix style setup, is that the code actually doesn't actually need to really differ at all from what you originally had, as long as you go in and double check that the scale of the priors makes sort of sense for what your data is. So if we go back to the R, 64, blah, blah, blah. That will go through. So now we'll have beta 1, which is the intercept, beta 2, which is the main effect of A versus B, beta 3, which is the main effect of 1 versus 2, and beta 4, which reflects the interaction. So how did I actually set up this data in the first place? Let's see. If I recall correctly, I've made it so that within the level of there should be an interaction. Within the level of A, there's a 1 versus 2 difference. Within the level of B, there is no difference. You can think of the main effects there. I think that works out to being both having a main effect. I can't recall. Certainly, yeah, when we look at the the two betas that reflect the two main effects, they both sort of, oh no, yeah, looks like there's a bit of a main effect of 1 versus 2, probably driven by this large difference here. Not so much an effect of A versus B, but all that is moderated by the fact that there's this interaction here. Oh, well, the interaction includes a little bit of the 0 is within the 95% credible interval despite the data being generated. So that's sort of a scenario of power and how much data I generated for each group. So we can actually take a look at what the actual estimates were for each of these things, because it's a little bit harder. So, I mean, this is like your typical ANOVA table or something like that, where you have something for each the contrast of interest, each thing of interest and their interaction. If you want to actually look at the means, you can do that. So I think I did this a different way. Yeah. So this gets all those groups with all their so you can look at the confidence intervals associated with each comparison. So there's group A1 versus A2, group B1 versus B2. We made that be in effect, that not be in effect. A1, B1. Oh. This is an error that's associated with the RGUI. I think I did a zoom on my trackpad. A2, B2. So you can get and you can also just get the point estimates and confidence intervals for each group individually if you wanted. But yeah. That was mostly to demonstrate how easy it is to, once you go to the matrix form of the STAN models, it's very easy to then extend to higher order designs without actually changing the model at all. You just have to learn how to structure your data with the and set the contrasts appropriately. Yeah, okay. Let's actually create this as data we already have. Instead of creating this as a list, I'm going to copy it up here. So these two things I don't need. So we're going to say, why is that? But so I'm going to repeat A this number of times. Oh. Make it a little bit more readable. B number of times. And then B. So I should be able to just copy this, shouldn't I? No, I'm just going to copy this. Okay, so let's say we have this. So we would have a situation where, again, this is between subjects designs, so we'd have a column for y's and a column for what bar 1 level each y was, and a column for what bar 2 level each y was. Sometimes R would have turned this into, well, we've kept it as a number if you actually read that data in. But I explicitly have turned both into factors. Another way, you may have known this already, but another way of seeing like what the internals of a data object is by using the str structure command. So it's saying it's a data frame. It's got 120 observations of 3 variables. So 120 y's, 120 var 1s. So and it's a factor with 2 levels, A and B. This other one's a factor with 2 levels, 1 and 2. A trick to get these contrasts. So let's just try to create x again. So x equals data.frame. Intercept equals 1. I only put 1 value there, but I'm going to give some other columns that have more than 1 value, and that data frame is smart enough to know to extend this one, just repeat its contents until it fills the number of rows that the other columns have. So if I want to be computing this contrast just from the data that I have there, because maybe this data was resorted or whatever, what I can do is I can say as.numeric my data bar 1. So that's A and B. What does it mean to take a factor whose levels are labeled A and B and turn it into a number? How is it going to do that? Well, what a factor is, it's actually stored as a series of numbers that have associated labels. So by default, it orders them alphabetically. So level A is going to have a number 1 associated with it. Level B is going to have associated number 2. So if I just ask for the number part of that combination, it's going to give me 1s and 2s. But I want negative 0.5s and positive 0.5s. Well, that's easy to do. We just subtract 1.5. 1 minus 1.5 is negative 0.5. 2 minus 1.5 is 0.5. So that's going to give me the same as if I actually done all that by hand. In contrast to, similarly, I just do that, and x equals x. Oh, just copy. So that little bit will do the exact same as I had up here, where I created this from my knowledge of what numbers should be going there. Here we just assume no knowledge. We created this data frame. We pretended that at this point here, okay, now forget how my data was. So even if we didn't have any knowledge really about how there's this sort of repetition format for my data, this would have still got out the proper contrast matrix. Well, so this was a little bit, yeah, the intention for, I guess, these sections was mostly to get you familiar with some of the Stan syntax and some of the sort of underlying ideas of establishing priors on parameters that you might have a little bit of knowledge on, and priors for differences centered on 0, that sort of thing. We'll get into really, but they were otherwise very boring models. Now I showed you some things where like you could not make the homogeneity variance assumption, things like that. Or you can use heavy-tailed distributions to take care of outliers. But we'll get into really cool stuff next week when we start talking about. I'm actually probably going to skip over the simple within subjects scenario and go straight to the more typical data. So within subjects, the data that it's very rare that we make one observation from one person in one condition and then another observation from that same person in another condition. Much more frequently, we make 100 observations from the person in one condition and 100 observations in another condition. Because we know people are noisy data generators and we want to average out the noise. Well, typically when we do our frequentist stats, we literally take an average, but I'm going to show you tools where you don't need to take an average, and indeed it's advised that you don't take the average, and these models will be a lot less restrictive than standard frequentist tools. Like you have the assumption of sphericity when you talk about repeated measures ANOVA. We won't need that assumption. Yeah, and we'll be able to do things like look at correlations